Hey folks, today what we're going to look at is we're going to look at a breakdown of a lab where we are reacting magnesium with an acid to produce hydrogen gas. Now we are using a pneumatic trough with a graduated cylinder, and if you want to see a previous video on how we set that lab up, you can go to the video linked. What we're going to be doing is we're going to be filling up this graduated cylinder with water, inverting it into a pneumatic trough, and then bubbling the hydrogen gas that's produced from this reaction in an Erlenmeyer flask into that graduated cylinder, and then measuring the gas to see what we've produced. What we want to try to do is determine the percent yield. So in order to do that, the first thing that we're going to have to do is we're going to have to find which of these reactants is our limiting reagent. From there, we can determine the theoretical yield. So step number one is to find your limiting reagent. Step number two is determine your theoretical yield. Now, what we're going to do is we're going to do something a little bit different here because we're going to determine the molar volume. So the theoretical yield, we will try to do in liters, okay? And we're going to need to use our PV is equal to nRT equation for this because what we can see is that our temperature and pressure is not a standard one, meaning it's not at STP and it's not at SATP. It's 23 degrees Celsius and 98.14 kPa. So we are going to have to use our ideal gas law, our PV equals nRT, in order to figure out the volume for our theoretical yield. But to standardize things, what we're going to do is we're going to do a molar volume. And what we're going to do is we're going to say our liters of H2 divided by our mole of magnesium. So essentially what we're trying to figure out is how many liters of that H2 gas is produced per mole of magnesium reacted. And this is going to be our molar volume and our theoretical yield. Next, we're going to find our actual yield, and we're again going to do our molar volume. So molar volume in the amount of liters of H2 per mole of magnesium. Now, the mole of magnesium used in this step and this step will be the same, and that's the one that we're going to find from our limiting reagent calculations. But our volume of H2 in our theoretical yield is going to be determined from our limiting reagent. Right? It's going to be determined from here. The liters of H2 found in our actual yield is the actual volume that we've collected. It's going to be this amount right over here. Okay, so there's a couple of things there. And then the last thing is that we need to figure out our percentage yield, which we already know is our actual yield divided by theoretical yield times 100 to get a percentage. So let's get started on this calculation. First things first is that we need to determine our limiting reagent. So if you wanted to go through a little bit more explanation about limiting reagent, you can visit one of my previous videos. Let's just get started into this. So I like to arrange it so that we go across the page, make things nice and organized. We're going to break up our two reactants, which is Mg and our HCl. So Mg, we had 0.0296 grams of this. So 0.0296 grams. And we're going to need to convert this into moles. So we need the molar mass of magnesium, 24.31 grams per mole. And if we do this calculation, we will get 0.001217606 mole of Mg. Okay. Perfect. Now for HCl, in order to find moles, HCl is a concentration and a volume. So in order we need to do that, we need to use our C is equal to N over V equation, but rearrange it for N is equal to C times V. Now remember that the volume is in liters. So 10.00 ml divided by 1,000 is going to be 0.01000 liters. Okay, so let's use these values here, and again, I'm going to change this big M into mole per liter. It's the same thing, but it just gives me the opportunity to cross out some units. So we have 0.500 mole per liter multiplied by 0.01000 liters. And now my liters are going to cancel out, which means I'm going to get moles, and we're going to have 0.005000 mole of HCl. Now, I like to carry out the zeros just so I can remember my significant figures. But if you want to truncate it and then bring those back in a little bit later on, that's absolutely fine. Now we are looking for the theoretical yield of the gas. So we have to go back to our balanced equation because we're going to need a mole ratio. Remember that in order to do this mole ratio, we are going to want to see our moles of Mg on the bottom in this case, and moles of HCl on the bottom here, because we want to cancel those out. And our moles of H2 will both be on the top because we want to compare how much each of these reactants will make of that H2, and the one that produces the least is going to be our limiting reagent. So again, we need our balanced equation for this. And to balance that equation, we need a 2 there, and we're pretty much good. So that 2, we're going to have that. We have 1 mole of H2, 1 mole here, and 1 mole here, right? So this is a 1 to 2 to 1 to 1. Now, we don't really put those 1s there, but just to see where we're getting those 1s from. This will allow us to cancel out our moles of Mg, and we are going to get the same number here, 0.001217606 mole of now H2. And then here, we're going to divide this number by 2, and what we're going to get is we'll get 0.002500000 mole of H2. Okay, so let's take a look at where we are. What this is showing us is that if magnesium, if this magnesium, the 0.296 was to react, it would produce this much H2. And if this concentration was to be the limiting reagent, it would produce this. Now, the one that produces the least amount of reactant is going to be, or the least amount of H2 is going to be our limiting reagent. And what we can see is that 0.01 is less than 0.02. And so our limiting reagent or our limiting reaction is going to be magnesium. So we are going to base our theoretical yield calculations off of that first calculation. So the actual amount of H2 that's going to be produced is this right here. It's going to be 0.001217606 mole of H2 that is actually going to be produced. Now we want to calculate our theoretical yield in terms of volume in liters. And so because our temperature and pressure is not standard, we need to use our ideal gas law. So our ideal gas law is PV is equal to nRT, and we are solving for volume. So to rearrange that, V is equal to nRT over P. Perfect. So our moles of H2 are the ones that we just found. And so that's going to be 0.001217606 mole of H2. Now our gas constant is dependent on how you're measuring pressure. If you're measuring kPa, you're going to be using one gas constant. If you're measuring in atmospheres, you're going to be using a different gas constant. In this particular case, we are measuring in kPa. So we are going to use 8.314 liters kPa over mole Kelvin. And then our temperature in Kelvin. Now, right now, we have our temperature as 23.0 degrees Celsius. To convert Celsius into Kelvin, we need to add 273 or sometimes 270.16, depending on what you want to use. I'm just going to use 273 for the purpose of this demonstration. And so 273 plus 23 is going to give me 296.0 Kelvin. Perfect. Now our pressure that we measured is going to be 98.14 kPa, 98.14 kPa. Now what's going to happen is that we're able to cross out a number of these units. Our moles cancel out, mole, kPa, kPa, Kelvin, Kelvin, and we're going to be left with liters, which is the unit that we do want. If we do this entire calculation out, we are going to get 0.030532506 liters of H2 produced. And that right there is our theoretical yield in terms of our volume. Now, what we're going to want to do is we are going to want to calculate the molar volume. So how many liters of H2 is going to be produced per mole of magnesium being reacted, magnesium being our limiting reagent. And so what we're going to do is we're going to go back and we're going to highlight the value for that limiting reagent. This is how many moles was consumed. And remember, the limiting reagent is always going to be the one that gets consumed completely. And so we're going to use this in order to do this last calculation. We're going to take this value and we are going to divide our volume of H2 produced by the moles of magnesium that were consumed, mole of Mg. All right. So now, if we do this out, what we're going to get is, I'm just going to go to 2 decimal places for now, and we're going to have 25.07 liters per mole. And this right here is our theoretical yield for our H2 gas. So we are producing 25.07 liters of hydrogen gas per mole of magnesium reacted. That's our theoretical yield. Now, what did we actually produce? So let's go back over here, and the actual amount of hydrogen gas that was collected was 29.75 mils. So 29.75, so our volume is 29.75 ml of H2 collected, right? So this is going to be part of our actual yield. First things first, let's convert that into liters. So 29.75 ml divided by 1,000 milliliters per liter, and we're going to get 0.02975 liters. Perfect. So just like we did in the previous step, and this is again of H2 gas that was collected, and remember that we used our 0.296 grams, which again was this value in moles. So we're going to use that same value to calculate the molar volume for our actual yield. So 0.001217606 mole of Mg. And if we recalculate this out, what we get is we get 24.43 liters per mole, and this is going to be our actual yield. Okay? So it doesn't really matter about what the unit is for theoretical or actual yield. We can do this in moles, we can do this in grams, in liters, in molar volume. It really just depends on what the question's asking for. In this particular case, we want to see molar volume. Now, perfect. So we have our actual yield, we have our theoretical yield. What we want to do next is calculate our percentage yield. So Py is equal to Ay over Ty times 100. And that means that our actual yield is 24.43 liters per mole, and our theoretical yield is 25.07 liters per mole. These liters per mole will cancel out, and we're going to multiply by 100. And if we do that, we will get 97.4%. Now, when we're looking at this, our significant figures are going to be based on the least amount. And so we have 3, 3, 4, 4, 3, and 4. So 3 is going to be the least amount, and it's 97.4 is where we're going to stay. So that's a pretty good result. 97.4% of what we should have gotten, we actually did get. The difference could have been simply there was maybe gas left out in the tube. Maybe it didn't simply react all the way. There was a measuring error in terms of how much something was weighed. Obviously, the resolution of our scale is going to also have an effect on that as well. So there's a number of different things that might play into this, and just simple error as well. But that's a pretty good result, and that's it for this. Thanks for watching.